Greetings to Dr. Cho and all the audience that are watching this presentation. Today we from Group 8 will be presenting our project on predicting the state of charge and battery temperature in electric vehicle using linear regression. Let me introduce myself. My name is Teo E. Yang and my team member including Li Zishi, Abdullah Masood Rashid Salim Al-Hinai, and Li Yongqi. This assignment was part of our data analytic course. Let's begin.
Professor, my name is Abdullah Al-Hinai. So now I will present to you the introduction about our project, which is electrical vehicles. So the adoption of electrical vehicles is increasing worldwide. The Norway and China are the leading for this way. Norway achieved around 80% of EV sales in 2022, and China reached 22%. This growth is supported by substantial government studies and investment in infrastructure and battery technology. However, there is a lot of challenges such as battery aging and capacity degradation, which is reduced by approximately around 2.3% per year. The thermal management issue can impact efficiency and reliability. So, accurate production of SoC and thermal characteristics are critical for maintenance, performance, and safety. Machine learning solutions such as ANNS and GPR have proven effective in addressing these challenges.
Now, let's discuss the research problem. In our research, we will focus on using linear regression models to predict the state of charge of battery and battery temperature. The primary objective of our research is to enhance the efficiency and reliability of electric vehicle through data-driven methodologies.
Thanks, my friends. So in this slide, I will explain about the literature review. So as you see, we reviewed around 7 papers with publication years 2021 to 2023. To find this paper, we do a lot of research, but also we used some keywords that help us to find it, such as battery temperature management, state of charge prediction, linear regression, machine learning in EVs, and finally the battery capacity prediction. So right now, let's have a look at the details analysis of these papers. In this slide, I will explain about methods, and the other things my colleagues will explain it. So, in literature review highlights various data analytics and machine learning methods used in battery management. There is a lot of studies that have been utilized ANNS and linear regression for battery temperature management. Also, a lot of techniques used, such as SiC-to-SiC and GPR, have been employed for battery capacity prediction. Furthermore, the various regression techniques has been forecasting driving rank and diagnostics fault. So right now I will let my colleagues to complete the other things in this slide.
Now let me introduce the challenges. Several challenges have been identified in the literature. These include issues with data collection, preprocessing, and model complexity. Data quality and completeness are also significant challenges, as well as the influence of multiple variables on driving range prediction. What about algorithms? The common algorithms used in the review study include agricultural neural network, linear regression, segment-to-segment, and GPR. These techniques are primarily focused on capacity prediction and fault diagnosis, demonstrating their effectiveness in enhancing EV battery performance.
As stated in our research focus, we choose a linear regression model for battery state of charge and temperature prediction. We choose regression model for several reasons. First, they are suitable for continuous prediction like state of charge and temperature. Second, the linear relationship assumption simplifies the model and aligns well with battery processes. Third, regression model offer easier interpretability of coefficients, providing clear insights into how each features impact performance. They also serve as straightforward baseline model and are computationally efficient, making them scalable for large datasets and real-time applications.
Now, let's jump into our simulation. There are 3 critical steps in our simulation. For the first step, we partition the data into 70% into training and 30% for testing. This strategy ensures our model can be evaluated on unseen data. This is to prevent overfitting and ensuring better generalization.
Now, the second step is linear regression model building. We built our linear regression model using the training data to predict state of charge and battery temperature. Linear regression was chosen as our baseline model due to its simplicity, interpretability, and computational efficiency. Now, let's move into our third step, the model performance evaluation. We have built some function for the evaluation metrics and diagnostic graph plotting. We evaluated our model's performance using several metrics. Now, let's move into our code. The mean squared error MSE to measure the average squared difference between predicted and actual values, and the root mean squared error RMSE, which is easier to interpret. The mean absolute error MAE to measure the average absolute difference, and the R squared to indicate the proportion of variance explained by the model. The last, the p-value to assess the significance of predictors. Additionally, we used visual assessments such as true vs predicted values, residue plots, and residue histograms. Now, let's discuss the simulation result.
Now, let's discuss the result. We'll first look into the model performance metrics. Let's first look into the state of charge prediction result. The results are as follows. For the MSE, we get 24.420A. For the RMSE, we get 4.9417. For MAE, we get 3.6168. And R squared, we get 0.9281. Our p-values indicate that most of the predictors are highly significant. And the high R squared values show that our models explain 92.81% of the variance of battery SoC. And the low RMSE and MAE values indicate that our predictions are close to the actual values. Now, let's look at the result for battery temperature prediction. These results are less promising. MSE is 16.5002. RMSE is 4.0620. For the MAE, we get 3.4513, and R squared we get negative 0.1463. The calculated p-values also discussed below. The p-values indicate that most of the predictors are highly significant. However, the negative R squared values show that our models perform worse than a mean prediction. Thus, despite the low RMSE and MAE, the predictions are unreliable. Now, let's look into the graph analysis for the battery SoC prediction. We have 3 graphs here. Let's discuss it one by one. For the first graph, the predicted values closely follows the true values, demonstrating a high model accuracy. And moving to the second graph, which is residual plot. The x-axis is the predicted values and the y-axis is their residual. The residual plot shows a non-linear relationship and non-constant variance. The spread of the residuals increase and decrease with the predicted values. It means the assumption of the constant variance of error is violated. This can affect the efficiency of the estimates and the validity of the statistical test. Now, let's look at the third graph. The residual histogram approximates a normal distribution. supporting the model's validity with minor deviation. Now, we come to the graph analysis of battery temperature prediction. For the first graph, there are significant deviation between the predicted and true values, indicating a poor model accuracy. And for the second graph, the residual plot shows a non-linear and non-constant variance also. It highlights the model fit issue and potential bias. And for the third graph, we can see that the two peaks are showing in the graph. This suggests that there are non-normal distribution, indicating the need for improvement in capturing the variability. If the residuals are not normally distributed, the validity of p-values and confidence interval is compromised. This will affect the reliability of hypothesis tests and the confidence in the regression coefficient.
To improve our models, we recommend several enhancements. First, we should explore nonlinear models such as decision trees, random forests, and neural networks to capture more complex patterns. Second, we can engage in feature engineering and apply transformations to create new features and improve accuracy. Third, regularization techniques like lasso and reach can help prevent overfitting and enhance model stability. Fourth, using cross-validation will ensure our models generalize well to unseen data. Finally, pooling decision trees can reduce model complexity, avoid overfitting, and improve performance.
In conclusion, our linear regression models predict SoC with high accuracy, supported by a high R-squared value and low RMSE and MAE values. However, addressing nonlinear relationship in the residuals can further improve the model. Conversely, the battery temperature prediction model is inadequate, as indicated by a negative R-squared values despite a low RMSE and MAE values. This suggests overfitting and poor generalization. Significant improvements are needed to capture the nonlinear patterns and reduce bias. That's all from us. Thank you for your attention.